plastic property, an important word is permanent. And okay, so for the midterm, I won't give the multiple choices question. So mostly the midterm will be either a composite problem with some calculations, step-by-step calculations, or ask you to explain some concepts. Okay, so there's no multiple choices. And for this kind of conceptual content here, like what is the elastic property, what is the plastic property, this kind of thing, I may have a quiz after the spring break. So we have a spring break from, I think from 29, 30, from 30 to 6th of April. So after that, I will have another quiz. So now you get used to the quiz, right? Because, you know, quiz 2 is like pretty good. Seems like most of you got the full marks, right? So similar, you'll get used to this kind of assessment pattern. So this kind of conceptual check, I would like to put it in the quiz. So for midterm, you just need to focus on more homework assignment-like problems. Okay. Oh, by the way, I upload the homework. Don't forget. Okay. Well, so that's what we learned last time, and we also reviewed some of the engineering scenario where stress and strain relationship will take place, like how the external loading apply to the specific solid object and how the solid object deform its shape according to the types of force applied, right? And last time, in the end, we give formulas to calculate stress and strain. So here we put an adjective, engineering strain and engineering stress, right? And be careful, it defined always with respect to the reference geometry. For stress, the force divided by cross-sectional area defined in undeformed shape. And for engineering strain is the relative shape change. Here for length change is always compared with respect to the original length. And this is the original width, okay? For that, maybe I don't use this now. I will use it later. So today we are going to discuss the stress state. This is also a review of your solid mechanics. I'll just choose part of important knowledge that taught in solid mechanics may be useful in this course. So here, if you have a piece of material, this blue material, okay, so this is a solid material, and this material is under loading, and this is axial loading, and this axial loading is the tension, right? Last time we discussed, and this is a normal force, normal loading, and normal force give you normal stress, and normal stress will change the length. So here, since it pull in this way, so it will elongate the material. Okay, so depends on how the element you draw. If you draw a small chunk of material as a cube. So this is not the crystal structure, cubic structure. Okay, this is just a random piece of material that we take it out. And we take it out, we look at the stress states. I think you already analyzed that stress state in solid mechanics 1. Okay, so this stress state, we call it the principal stress state, if you remember. All the shear vanishes, left with only normal stress state. So that is the principal stress state. And this is a very well-selected orientation, right, from this piece of material. Now, if we cut it through some orientation with an angle tilted a little bit, angle theta here, and now we can draw another element. Sometimes we call it element, sometimes we just call it like small chunk of material. We take it out, and then we do force analysis. I think you did that for like both fluid mechanics and solid mechanics. I don't want to repeat that again and again. It's very tedious and technical. So let's just look at a high level. So to make sure the force balance in this different state with different orientation, you need to have the normal stress, which is the sigma prime here, with different value. So here, internal piece of material should be in equilibrium everywhere, from inside to outside and at the surface, right? So if the pulling of the external stress or external force is sigma, or sigma is calculated as force divided by area, becomes like stress kind of unit, right? So if this magnitude is sigma, then this red arrow also corresponds to the magnitude of normal stress, sigma. If it rotates, not it rotate, if we choose a different chunk of material with different orientation and we take it out, and then we still can do all the force balance kind of calculations that you have already done many, many times in other courses. And in the end of the day, you'll still have this kind of normal stress and shear stress, okay? This shear stress not vanish it. That means this is not in principal stress states. All of this is just a review. And here, you still have normal stress but with different value. And you still have the non-zero shear stress with some other value, non-zero value. And then here, this formula tells how do you calculate the values of a different orientation with respect to the cross-section area orientation, horizontal orientation through angle theta with the magnitude of the external loading, okay? Did you learn this formula already? Good. So you just need to know how to use it, okay? So in the most mechanical test, we tested the longitudinal pulling or longitudinal compression. We call it axial loading condition. Okay. Then, in the experiment, what you can sense or what you can measure is the magnitude of this applied force or applied stress, okay? And then, if you want to know at any place inside the material, like orient differently with an angle theta differ from the horizontal orientation, you use this. And be careful, this theta is this angle, not some other angle. So this angle will be pi minus theta. So here, maybe sine becomes cosine, cosine becomes sine. So you need to be careful when you calculate this. Okay. So now, maybe it's still not so close to the course content of material science, right? So when we discuss sleep, when we discuss how material plastically deform, this kind of concept will slowly play a role. So I just listed here. It's still a part of the review. And now, by some like calculation here, I didn't put a calculation here. If you do a calculation, something like, if you have something written in terms of sine theta, cosine theta, if you want to do a maximize or minimize kind of calculation, do you know how to do it? So this is 1/2 2 sine 2 theta, high school thing. And we know sine 2 theta always less than 1, so this always less than, what is that, what I'm doing? Yeah, something like that. That's it. And here, the equal sign will be satisfied when 2 theta equals to pi over 2 plus 2 n pi, with n is integer, right? Something like that, right? So this is like 90 degree. And theta equals to 45 degree. Because this is too trivial, I didn't put it here. Okay? So that means at some angle theta, at some angle this theta here, the shear force reach the maximum value. Because I leave this blank for you to write. Okay? You can write this here. So you can say, well, the shear actually very much determine the plastic deformation. Okay. And also, this plastic deformation will determine the fracture of metals. Okay, or degradation. Or degradation of metals. So this content is very important in material science. Usually it's not the normal force cause the material break. It is the shear force cause the material break. That's why we need an expression of the internal. So this is the internal shear stress. So this is something inside the material, okay? And this is something outside, right? So this is an external force that applied to the material. So this kind of applied force will cause the material fracture or break. Then how? What is the mechanism? The mechanism usually relates to the internal shear stress along certain interface, which is the yellow interface here. Okay? And then we may ask at what angle, at what orientation this value reach the maximum value. At 45 degree, this one reaches the maximum value. If that material intrinsic strength is lower than this value, that material will suffer plastic deformation. If the applied force increase, like if applied force, this is applied. Okay, this is applied. Okay, this is applied force or applied stress. If the applied stress keep increasing and this keep increasing, and if this is more than the strength of the material or yield strength of the material, and material not only just yield or plastic deform, and if you keep increasing the level of that stress, it will like get degraded or finally fractured. Okay, so this is an important quantity here. Do you know that if we have a building, right, and that building is very, very old, and we need to like set some bombs to demolish that building, or like maybe in Japan there are like a lot of earthquakes, and if a building built up on an active continent where the earthquake is very active there, and when there's an earthquake, then the building will like suddenly break, right? So do you observe that, like how the building break? So usually, if this is the land, right, and then if this is oscillate or something, or if you set some bomb inside this building, usually this building will crack, like along 45 degree. You can easily search like a YouTube video. You just type like a demolish of a building, right? Usually you'll see the building is just breaking this way. So it's like crack here and crack here, crack here. The crack always like this. So it's actually the internal shear force cause the material break, not the normal force cause the material break. Okay, so now once we know the relation of geometry to the deformation strain and force to the calculation of stress, now next we need to understand the stress and strain relationship. Actually, this relationship tells like how material responds to the external force, and sometimes we call it constitutive relation. Okay. And in this course, in this chapter specifically, the constitutive relation is a kind of relation between the strain and the stress. So here, as an example, if we have a reference configuration, undeformed configuration here, if we apply the load, this material will get elongated and shrinked transversely. In 2 dimensions, we have 4 components for stress, 4 components for strain. I believe this has been already taught, right? I don't need to explain that. You already know it, okay? In 3 dimensions, we have 6 components for stress, 6 components for strain. Actually, why I say 6 independent components for 3D. So in 3 dimensions, you will have 3 normal stress, 1, 1, 2, 2, and 3, 3. And you'll have 3 shear. That's like 1, 2, 1, 3. 2, 1 is equal to 1, 2, so it's the same. And 2, 1, 3 is the same as 3, 1 is the same as 1, 3. And then you have 2, 3. So although this matrix, or sometimes people call it the stress tensor, has 9 components, but because this one is a symmetric, it's symmetric. So its ij component equals to ji component. So if you draw a stress state for 3 dimensions, and you have normal stress component, and you have shear, they are in this orientation but the same magnitude, and you have this kind of thing, and you have this kind of thing, right? Right. And then if this is reduced to 2 dimensions that I draw in the slides, so you still have like the normal component, if this is reduced to 2 dimensions, if you draw the stress state, you'll have normal component, right? And you'll have shear component, something like this. And these 2 must equal. That correspond to sigma 1, 2 and sigma 2, 1. Sigma 2, 1 must equals to sigma 1, 2. Sigma 1, 1 and sigma 2, 2, they correspond to normal. Okay? So this is the normal stress. And the normal stress causes the normal strain. And the shear stress causes the shear strain.